Good day, I am Kok Yu Jie from Group 6 Section 5 and my team member Teo Yun Je, Yap Boon Jie and Siti Zulaikha. In this video, I would like to introduce to you our group assignment, which is ALU designed for Risc-V CPU. RISC stands for Reduced Instruction Set Computer, which is part of the computer architecture called Instruction Set Architecture. It is designed and optimized to use fewer instructions, which enable the processor to use less power, makes them ideal for smartphones, cameras, smartwatches, and all kinds of IoT devices. On the other hand, 5 is based on the RISC standard that anyone can use to design their own chips without paying license fee. At the heart of a Risc-V processor, an arithmetic logic unit ALU is responsible for executing arithmetic and logical operations. It embodies the principle of RISC, which promotes simplicity and efficiency due to the basic operations of ALU. This ALU design was designed using Intel Kratos Prime software. The ALU can be divided into 3 parts, which are the 4-bit 4-to-1 multiplexer, 4-bit adder, and D flip-flop as a register. Firstly, there are 2 4-bit 4-to-1 multiplexers. The upper one acts as an input A selector, while the bottom one acts as an input B selector. Before that, we have to design a 4-to-1 multiplexer with logic gates. This 4-to-1 multiplexer is designed to select 1 out of 4 input signals for output, an input A selector, while the bottom one acts as an input B selector. Before that, we have to design a 4-to-1 multiplexer with logic gates. This 4-to-1 multiplexer is designed to select 1 out of 4 input signals for output. It is controlled by 2 selector lines, ASL0 and ASL1, that precisely determine which input is directed to the output. This allows ALU to choose the desired input for a specific operation. It consists of 4 3-input AND gates and 1 4-input OR gate. It has 4 inputs, A00, A10, A20, and A30, and the selector inputs, represented by ASL0 and ASL1. Determine which input is connected to the output line, A0. ASL0 is the least significant bit, while ASL1 is the most significant bit. Then we create a 4-bit 4-to-1 mask by using 4 1-bit input is connected to the output line, A0. ASL0 is the least significant bit, while ASL1 is the most significant bit. Then we create a 4-bit 4-to-1 mask by using 4 1-bit 4-to-1 multiplexer. Start from the uppermost 4-to-1 mask. Bit 0 of each input are connected to the input terminal, and till the bottom of 4-to-1 mask, bit 1, bit 2, and bit 3 of each input are connected to the input terminal ascendingly. B selector's working is similar to A selector, but selects input B0, B1, B2, and B3 according to the value of bit cell.
So I'll be explaining about the full adder. The figure above shows the logic circuit in a 1-bit full adder. It consists of 2 input XOR gate, 2 input AND gate, and 1 2-input OR gate. The input AI and BI are used to perform addition operation with input CI1, which is normally 0, GND, when undergoing addition, and 1, which is VCC, when undergoing subtraction. The value of input CI1 is dependent on the value of ALU op. The value of output SI is the sum of AI, BI, and CI1, which is calculated using 2 XOR gate with the following equation. The value of output CI is the carry that produced from the addition operation of AI, BI, and CI1. With the following equation, the working of the full adder is shown in figure C.2. Figure D.1 shows how to create 4-bit full adder with the function of subtractor by using 4 1-bit full adder and 4 2-input XOR gate. 4 1-bit full adder are cascaded and connected with the 4-bit output of A from 4-bit 4-to-1 mux at terminal AI. The 4-bit output of B from 4-bit multiplexer is connected to the XOR gate with input ALU op to perform 1's complement transformation if value of input ALU op is 1, which means the subtraction operation will be carried out. B is then connected to terminal BI of the full adder.
I will explain the design of the register. The output of the adder is connected to the D flip-flop. The D flip-flop is added as a register, which will produce the output same as the input according to the rising edge of the clock signal. When the clock signal is reaching a positive edge, the output will produce or change to the output of the full adder, which lies on the rising edge of the clock signal. For this case, a 4-bit D flip-flop should be used and connected in parallel to share a clock signal. Each flip-flop will store 1 bit of data and will be out there simultaneously when a positive edge clock signal.
For the waveform diagram part, the resistor will be activated and change or remind the output when the clock signal reaches positive edge. Example, when 0.5 microsecond, the clock signal is reaching positive edge. The ALU OP output was set as 0, which means this is an addition operation. For the A and B selector, the A cell and B cell input are 0, 0. So the first input of A and B will be selected from the multiplexer. In this case, the data that selected from A is 0011 and B is 0000. By adding both them up, the output will be 0011, and it had been verified as the output of the register. Other than that, when 2.5 microsecond, the difference is the ALUOP input and the SL B cell value. The input of ALU was set as 1, which means subtraction, and SLB cell are 0, 1, which means the second value was be selected. The value of A1, B1 is 0, 0, 0, 1 and 1, 0, 0, 0. So the data of B1 will be inputted and plus 1 to do the two completements, and finally adding up A and B with the output will become 1, 0, 0, 1, and that is shown in the timing diagram and proved correctly.